because we're looking at the rate of production of A and not of R. So the coefficient is the 1, not 1 or minus 1 for the forward reaction, plus 1 for the reverse reaction. If I were looking at RR, then I would have either plus or minus R coming in. Okay, so let's go through it. So for plug flow reactor, non-constant density, linear volume expression, I've got the third row, third column. So I've got tau 0 is equal to, well, let's divide by CA0, integral x in to x out, dxa over minus RA. What's minus RA? We have it right here. So I've got minus K1 CA. CA is CA0, 1 minus XA over 1 plus epsilon A XA. And right from here. And then I have a plus K2 times CR. CR, again, is CA0 from here, times M plus RXA, divided by the volume part, the same denominator. Let me finish, okay, you always just let me finish the algebra, then you can ask the question.
If you're doing minus R, you're going to have the signs of K1 and K2 reversed.
If I were doing it in terms of R, I'm sorry, what was the question?
You said it's minus RA, so don't you need to have the signs of K1 and K2 reversed?
Yes. Thank you. Okay, so one thing we can notice is the CA0s cancel. Again, the CA0s always end up canceling out for first order reactions. The minute something's not first order, the CA0 will stick around. And notice the denominators are the same. The denominator, the denominator. So this is equal to x in, x out, 1 plus epsilon A xa dxa divided by K1 times 1 minus K2m. And then I have minus xa times K1 minus plus R, K2R. And I can integrate this two terms. I do it in two terms. So the first term is just the 1, so I've got dxa over this. So that just gives me the log of the denominator with some constant coming in. So let's see, that looks like a log of K1 plus K2R xa divided by K1 plus K2R with a minus sign. Let's see if that's right. No, the log of the whole thing. K1 minus K2m minus K1 plus K2R xa. The minus sign, let's see if that's right. So I take the derivative, I get 1 over that times 1 times the minus sign. That's correct. From in to out. And then I've got epsilon A xa dxa. So then I have in, out, plus epsilon A xa dxa over, to simplify things, the writing, I'm going to call this alpha and this beta. So I don't have to write so much. Alpha minus beta xa. And that one, I guess I do by parts. That's a little bit of a mess. I guess we do it by parts. Is there an easier way of doing it? No. All right, so this is U. This is dV. du is equal to dxa, and v is equal to the log of alpha minus beta xa divided by minus beta. So this thing I'm going to call I, and I have I is equal to uv minus the integral v du. So uv is xa log alpha minus beta xa over minus beta, evaluate the limits, minus the integral of v du. So minus a minus is 1 over beta times the integral of log alpha minus beta xa dxa. And the integral of log x, actually let's just change variables so we'll make this easier. So I'm going to call this thing y. So I'm going to let y be equal to alpha minus beta xa. And dy is minus beta dxa. So this thing is just 1 over beta times the integral of log y. And now dy is dxa over minus beta. I'm sorry, so dxa is dy over minus beta. So this is dy, dxa over beta with minus sign, I just get a minus sign. dy. And this integral is just y log y minus y. So let's put these things together at the limits. So the answer, if we haven't made too many mistakes, is tau 0 is equal to, well, so this is minus log alpha minus beta xa divided by beta, evaluated the limits, and then I have plus xa log alpha minus beta xa over minus beta. This was, we said, y log y minus y. Okay, and then I have plus xa, epsilon a, times the integral I. The integral I is, I'm sorry, there's an epsilon a here, plus epsilon a, evaluated the limits. That is this term. And then I have plus epsilon a times this thing. So it's, and I have the minus sign here, so this is minus plus. So I've got minus y log y minus y. So that's alpha minus beta xa log alpha minus beta xa plus alpha minus beta xa evaluated from in out. Okay, so there's I did a fair amount of algebra here, but before you evaluate, you might as well just factor out the logs, so you don't have to evaluate the logs 100 times. And if I haven't made any mistakes, this just gives you tau 0 is equal to log alpha minus beta xa times minus 1 over beta, that's this, and then I have minus 1 over beta times xa. That's this term. And then I also have another term with a log, and I've got an epsilon times alpha minus beta xa. All this times the log, and then I have the terms without the log, which is really just this term. So then I have plus epsilon alpha minus beta xa, and all this is evaluated in out. So what you can see is you just get a transcendental equation with logs and linear terms. And you could plug in here, you can check the algebra. What I'm illustrating here is how you set up the problem and how you actually do it. And it's fairly straightforward. The algebra can be a bit tedious. Why are there any questions? Now, I want to stress something here. When you use the design equation, what I told you was the design equation was a relationship between a few quantities. What's in the design equation? The design equation, let's say for a CSTR or a plug flow reactor, if you look at it, what are the elements you have in here? You have a tau zero, which contains Ca0, V, and Fa0. So it contains a molar flow rate at the reference state, a concentration at the reference state, and a reactor volume. And it also contains X out, which are the product specifications. And it also contains the chemistry, the Ks, the kinetics. Okay, so typically, some of these things are known, and some of these things are unknown. In an undergraduate course, usually one of those things is unknown, and everything else is known. That's not the way it always works in real life, but that's the way it works in undergraduate classes. So if I give you a problem on some future exam or in your homework, or I give you some data for a reactor where I tell you all this stuff, but we don't know the kinetics, then you use that data to determine K. It's the only thing unknown. And then I might ask you to use that K in a different reactor. Well, in a different reactor, you know the K, and one of these four quantities is going to be unknown. I'll give you a problem where the Ks are given and the specs are given, and you have to determine one of these quantities. How big a reactor? How much can I flow through there? Etc. These are typical problems that you're going to get. But all they are, if you think of the design equation as a relationship between these three quantities, where this is a compilation of these three. Then the design equation says if there's only one of them that's unknown, you use the design equation to determine the unknown in terms of the knowns.
So, like, is the differential and integral method still applicable other than for batch reactors where you define like Ks?
The differential and integral methods are for how you use a batch reactor to investigate kinetics. So that's in terms of the batch reactor.
So usually, like,
You have to remember, generally, you're going to be, when you're dealing with the plug or the plug flow reactor or a CSTR, you're dealing with kinetics that are more well known than we had in the first chapter. So typically, you're going to know the order of reaction. You're going to know the form of the kinetics. What you may not know is the rate constant. But you know the order of reaction in the form of the kinetics, which you got from those methods from using the batch reactor, or the chemist got them for you. But when we get to these reactors, what you can determine typically are the rate constants. But now, of course, you can try to use these reactors to determine the kinetics as well. But then it's basically you guess the kinetics, you solve the design equation, you compare with the data. So you're really stuck with an integral method. If you're going to try to use continuous reactors, steady state continuous reactors to try to determine kinetics, you have much less flexibility. You're kind of stuck with the integral method. Now, of course, integral method in terms of plug flow reactor, because you integrate. For the CSTR, you don't integrate, but you solve algebraically.
So usually we're working in terms of either first or second order reactions for plug flow and CSTR.
No, those are just the examples I did on the blackboard. The kinetics are what they are. You can't say because I'm using a CSTR, I'm only going to allow first and second order reactions. That's not true. The chemistry decides what the kinetics are going to be. You don't decide. The chemistry decides. And typically you're going to use the batch reactor systems to try to determine the kinetics. What you typically usually once you get to the design, usually you don't start designing a steady-state reactor or flow reactor until you know the kinetics. The batch reactors are much more versatile for determining the kinetics. Now, it doesn't mean I wouldn't give you a problem where I ask you to, you have only a steady-state reactor and you gotta do what you gotta do. So I might ask you a problem where I ask you to use the steady-state reactor to determine something about the kinetics, but usually you determine the kinetics more in batch reactors because they're much more versatile. There, the versatility is important. Why do you use a continuous reactor? It's when you want to make a lot of something. When you're determining kinetics, you're not worried about making a lot, you're worrying about learning about the reaction. So they have different advantages and disadvantages. So the versatility is important because if you remember, there are all different types of experiments you would do to investigate the kinetics, and the batch reactor is good for all different types of reactions. You don't want to make a lot, you just want to get information.
And also, like, I think you would need a batch reactor in order to apply, like, method of excess and method of isolation, like different methods of learning.
As I said, the versatility of the batch reactor, it allows you to do all those different types of experiments that are much more difficult to do in analysis experiments in continuous flow. And the continuous flow reactor requires lots of stuff because you got to reach steady state. You start a reactor up, it's not in steady state. So no normal person would use a continuous flow reactor to determine kinetics. You would use a batch reactor. You use much less material. And it's more versatile.
No, I was just going to say.
The only abnormal people who do that are tests.
Yeah. I was just going to say that so if you, as a person who wants to produce something, the batch reactor is just a tool to find the kinetics. And once you know the kinetics, then you can use your plug flow or CSTR to produce your product.
There are times when you want to use a batch reactor in industry as well.
To determine the kinetics?
Batch, again, I told you, batch is what the choice for the kinetics in any case. But there are cases in industry where you want to use batch reactors also. There are some high value chemicals that you don't need a lot of. And there isn't constant demand. It may be seasonal. There may be only demand at a certain time of year for mosquito repellent. You don't need mosquito repellent in the winter. So, and you may not need tons of it. It may be a special kind for a particular type of mosquito you only get in one location. So you make a batch of it. So typically specialty chemicals, high value specialty chemicals that you don't need a lot of, but it pays for you to make them, certain pharmaceuticals. You make those in batch reactors because you don't need 100 tons of it. You don't know what to do with 100 tons. It's just too expensive. No one's going to buy 100 tons. So there are lots of things that go into your choice of reactor. All right. So once we are somewhat comfortable with the three types of reactors and how to do calculations, of which, did I give you a homework on this yet? Okay. If I didn't, I don't think I photocopied it out. I'll photocopy it right after class and leave it in my box. So there's a homework on that. What was the last homework I gave you?
2.
Okay, so I will give you homework 3. Homework 3. All right, I'll photocopy up homework 3. Yeah, which is all about this. Okay, so now, as we said, we're going to have a class on Friday, and we're going to have the exam Wednesday. Okay. Just because the exam was postponed, just because the exam will be next Wednesday, which is a long time after we finish the material, does not mean that it is at all intelligent to ignore this material until after the exam. In fact, if you do that, I guarantee you will fail the second exam. I guarantee you. You have to do this homework now. If you get too far behind, you will never catch up. So that's a word to the wise. Just because the test on the material through batch reactors isn't until next Wednesday doesn't mean that no material beyond that enters your brain before that. If you do, it will never enter your brain. Okay, that's a word to the wise. So therefore, you've got plenty of time between now and then. What I would suggest is that fact, why don't we do that? Why don't we make at least half these problems due on Friday? So that way you actually learn this material by then. So why don't we say there's going to be, there's a whole three columns of problems. So why don't we say, well, the second column is just one problem, it's just pretty wordy. 1, 2, 3, 4, 5, 6, 8, 9. There are 10 problems. Why don't we say the first column will be due on Friday? So the first 6 or 7 columns. That way you're forced to look at it before that. Okay, and that's whether you're here or not. If you're not here, make sure you get it. All right, so once we're comfortable with the idea of a single plug and a single CSTR, let's start looking at our choice of reactor. And how do you choose how do you know whether you're going to go with a plug flow or a CSTR? Let's assume you want to make a lot of something.